All right, let's talk about calculations. So say I do an experiment. Okay, I come up, I got an A plus B gives me C experiment. And the generic rate equation would be rate is equal to K, concentration of A, which is one of the reactants, to some power X, times concentration of B to some power Y. Okay, my goal here is now I want to know what K is, and I want to know what X and Y are in this rate equation. So we did an experiment. We had the concentration of A and B, and then we measured the rate. Okay, experimental 1, we held them both at 1 molarity for A and B, and we found the rate to be 1 molarity per second. In the second experiment, what we did was we held A constant to the same concentration as before. We doubled the concentration of B, and we measured the rate. We did this because any effect that A had on rate, it has the same effect on the second experiment, so any difference between the rates is all coming from B. Third experiment, we doubled A from the first experiment, and we went back to the same concentration of B for the first experiment and found the rate to be 1. Now we can determine the orders of these from this rate equation by inspection, or we do it mathematically. I'll do both. Okay, if it's easy numbers, inspection's quite simple, but if it's a little more difficult numbers, then you might need to do it mathematically. So looking at this, I need to look at 2 experiments and try to figure out what happened to the rate. So let's talk about Y first. Okay, I'm going to try to find the Y order. Okay, which 2 experiments would I look to determine that Y, that order for B? Okay, well, looking at it, experiment 1 and 2, okay, I'll see that the concentration of A stayed the same. So anything that happened to it's going to cancel itself out. So the only effect on rate will be from that B change. And we can see that the concentration of 2 to some power equals what happened to the rate, 8-fold rate. Okay, so 2 to some power is equal to 8. So what does that power have to be for that expression to be correct? I doubled the concentration of B and my rate went 8-fold. Okay, well in this case the only thing that could be true is that Y has to be 3. 2 cubed is equal to 8. If I want to know what the X is, by inspection, I got to look at 2 other experiments. So let's look at X. I'll look in this case, I'm going to look at 1 and 3. Why? Because then my B concentrations will cancel out. Now I already know what Y is, so I don't really need to cancel them out, but it makes the math easier if I do get them to cancel out, so I'll choose 1 and 3. I can see now that my concentration of my 1 and 3 doubled, but what happened to the rate in that instance? It stayed the same. Okay, it's 1 molarity in experiment 1 and 1 molarity in experiment 3. So my expression here is I know that 2 to some power of X is equal to 1. The only way that this expression can be correct, okay, is that 2 has to be 0. Anything to the 0 power is equal to 1. So doing it by inspection, I know that rate is equal to some constant K, concentration of A to the power 0, concentration of B to some power of 3. And typically A to the 0, we just eliminate it since anything to the 0 power is 1. That's by inspection. Okay, I'm just looking at the experiments and knowing what happens. Look at the change in concentration, compare that to the change in rate, and decide what the order is. Now, I can do it mathematically too if I can't see that visually by inspection. So let's look at that. Okay, we'll do the same thing. I'm going to try to figure out 1. Let's do Y first. I'm going to look at the concentrations and try to get 2 experiments that basically one of the species canceled out. As we said before, I'm going to do experiment 2 and 1. That way my concentration of A cancels out. All we're going to do is write the rate law expression of one over the other one and compare the data. Now I can do this because that rate constant is a constant. Okay, for any one of the experiment, that K is the same for experiment 1, 2, and 3. So basically they're equivalent values according to that K. So we'll just write the rate law of one experiment over the rate law of the second one. Okay, rate 2 equal to K, concentration of A, second experiment to some X, B, second experiment to some Y. Rate 1 equal to K, concentration of A1 to some X, B1 to some Y. Now I tend to write the larger numbers in the numerator, so I'm going to put experiment 2 because of the fact of that 8 is a larger number, I'm going to put that in the top because I can do math in my head with the larger numbers easier than I can with decimals. Okay, so I just by habit put the larger one on the numerator. You don't have to. You can put it the low one and do decimals and still come up with the same answer. So now all I'm going to do now is put in the data. Okay, well first off I'm going to combine. I know that a to the subscript 2 divided by a to the 1, they're both to the power x. I can combine terms and now put a2 over a1 is equal to the x power and b2 to the b1 to the y power, and I also see that in that process k is the same, so that cancels out. So I'll simplify it some. Now I'll put in my data. Rate 2 is 8 molarities per second. Rate 1 is 1 molarity per second. It's 1 molarity in both cases for my concentration of A, experimental 2 and experiment 1. And it's 2 molarity in experiment 2 for B and 1 molarity for experiment 1. Now I can do some cancellation. I can see that my units will cancel here. This whole expression will cancel. Doesn't matter what x is, 1 to 1 will be canceled out, which will leave me 8 is equal to the y. Now, I can see that the only way that this could be true is that y has to be 3, 2 to the cubed equals 8, but maybe I can't see that mathematically in my head, so I'm going to tell you what you need to do to determine this mathematically. What we're going to do is take the log of both sides next. I'll take the log of 8 and the log of 2 to the y. The next thing I got to realize mathematically, log 2 to some power, that power can come down to the front, okay, and be y log 2, and that's still equivalent. Okay, why I want to do this is I want to get log to the other side. So now I'll divide by log on both sides, and I get y is equal to log of 8 divided by log of 2. I put that in my calculator and I get 3. Okay, you got to realize though, I need to take the log of 8, get that value, and divide that by the log of 2, that value, to get 3. I can't cancel logs, and I can't cancel 2 into 8 and get 4. I have to get the numeric value of log of 8 divided by the numeric value of log of 2 to get 3, which is the same answer we got earlier. Now to do the x, I'm going to take the same two experiments we told before, experiment 3 and 1. Okay, and I will put experiment 3 on top. Okay, so we have our two rate laws. I'll now plug in the data. Okay, I got 1 molarity per second in both cases for rate 3 and rate 1. 2 molarity for the concentration of A for experiment 3 over 1 molarity for experiment 1. 1 molarity for both my experiment 1 and 3 for concentration B. Now notice I have the 3 there because I already solved for that in the previous part of this problem, but I really don't care the order there because I'm going to pick experiments that it cancels out. I want to simplify my math, so I want it to cancel out. So I'm going to pick 2 experiments that is the same concentration, that way it cancels on out, which it does in this case. And you notice the K's cancel as well. Continue on, my units cancel, so I end up getting 1 is equal to 2 to the x. Once again, the only way this is true is x is 0, but if you can't see that, we're going to put a log on both sides, and we'll take that x and bring it down, which would be x log of 2. Bring it over, I get log of 1 divided by log of 2. Put that in the calculator and I get y is equal to 0. So now I have my x and my y. Okay, same values I had before. But to finish this problem, I have to solve for k as well. So now I can plug in any sets of data, my whole experiment 1, 2, or 3, and solve for k. So let's go ahead and do that. I like choosing the first one. So I'll choose experimental 1 data. So it's just a case of plugging them in. So I'll take my rate law, which we said is rate is equal to k, concentration of B to the cube. Now do realize that we found out that A to the 0 was part of it, but anything that 0 is 1, so it's not part of the rate law anymore. We drop it off. So then I'll plug in my rate, 1 molarities per second for experiment 1. I'll plug in my concentration of B, which is 1 molarity. I'll now do the math. Okay, now realize that it's 1 molarity cubed. That means the whole 1 is cubed and the whole molarity is cubed. The whole thing's cubed. And then you have to cancel units. I get the 1 divided into 1 and I get molarity cancels. That changes this to 2. Which means that I have 1 over molarity squared second, which then mathematically 1 molarity minus 2 second minus 1. Thing to realize is if it's in the denominator, I can write it as a negative, okay, in my expression. Other thing to realize is when you cancel things, these are great, I got nice whole numbers. What if I have decimals? Okay, you got to realize when I'm canceling things, it's just the things in the numerator are positive numbers and the denominator are negatives. So in this case where I have m over m cubed, really what we're doing is we're saying I have 1 from that numerator 1 minus 3 in that denominator, which means it's a total of a negative 2. So my answer is molarity minus 2. So when you're dealing with exponents in the units in the numerator, those are positive numbers. The ones in the denominator are negatives. So you're just doing a positive minus the negative to figure out the overall unit. So my final answer, rate is equal to 1 molarity minus 2 second minus 1 concentration of B to the cubed. So if I know the concentration of B, I can determine the rate. This equation allows me to do that for any concentration of B. I can determine the rate of that experiment. So we got another example. Iodine ion is oxidized in acidic solution to triiodine I3 minus by hydrogen peroxide. Okay, a series of 4 experiments were run at different concentrations and initial rates of I3 formation was determined. So we determined the rate of I3 formation and we varied the concentrations of the species, holding some constant and changing other ones. From the following data on the next slide, I want to obtain the reaction orders with respect to the hydrogen peroxide, the iodine ion, and the hydrogen ion. We're going to calculate also the numerical value of the rate constant K. I want the entire rate law, which means I need to figure out the K, the X, the Y, and the Z. Okay, I want the entire rate law, which means if I know the concentrations of these species, I can figure out the rate of reaction at any point. So here's your data. Okay, experimental 1, we have concentration of hydrogen peroxide 0.01, I minus 0.01, hydrogen ion 0.0050, and we measure the rate. The experiment 2, we can see we hold the I minus and H plus constant, but we change the concentration of H2O2. Experiment 3, we change in the concentration of I minus and holding the other 2 reactions constant. Experiment 4, we change H plus, but we hold the other 2 constant. And we measure the rate in all instances. So the first thing I want to do is let's figure out that X. Let's figure out that order with respect to H2O2. Which experiments am I going to compare to try to figure that out? Well, if I look at experiment 1 and 2, okay, we can see that the concentrations of my I minuses and my H pluses are the same, so they have no effect on rate. So any change in my H2O2 will be affecting my rate. So I can look at these 2 experiments to figure out that order with respect to my hydrogen peroxide. Looking at the data, you can see that I doubled the concentration of H2O2, my hydrogen peroxide, and what happened to the rate? It also doubled. That's a linear relationship, which means that that order must be a power of 1. Okay, so that's by inspection. Now what if I needed to do it mathematically? Let's do that. I would compare experimental 2 to experiment 1. Remember, I like putting the larger one on top, so I put in the data. 2.30 times 10 to the minus 6 molarities per second over 1.15 times 10 to the minus 6 molarities per second equal to the K's. Concentration of my hydrogen peroxide 0.02, 0.01 to the X, I minus 0.1 to the Y's, and H pluses 0.05 to the Z's. Notice in this process, my units cancel on my rates, my K's cancel, my Y's cancel, and my Z's cancel. This leaves me an equation of 2 is equal to 2 to the X, which has to be 1, or doing it by logs, log of 2 equals X times log of 2, X then equals to 1. So we know the order with respect to the hydrogen peroxide. Let's move on to the next one. Let's look at I minus now. So so I'm going to concentrate on I minus now. Which experiments will I choose now? Well, I want H2O2 and the H plus to cancel out, so we're going to take experimental 1 and 3. You can see my concentrations will cancel out, so anything that's occurring with my I minus will be affecting my rate. Comparing experiment 1 and 3, we see that the I minus concentration doubles, and at the same time the rate doubles, which then linear relationship once again means we have an order of 1. This implies the first order dependence with respect to I minus. Now let's look at this mathematically. Experiment 3 to experiment 1, put in the rates, 2.3 times 10 to the minus 6 over 1.15 times 10 to the minus 6 molarities per second, equal to K times 0.1 molarities for my hydrogen peroxides. I minus is 0.02 versus 0.01 to the Y, and the H plus is 0.005 in both cases. We see what happens here is my concentrations of my H plus cancels, concentration of my I minus cancels, K's cancel, my units cancel, leaving me with 2 equal to 2Y. Once again, Y is 1, but if I can't see that, let's do the log. Log of 2 equals to Y log of 2, which then gets me Y is equal to 1. Last, let's look at H plus. I need to pick 2 experiments that I hold H2O2 and I minus constant. That's going to be experimental 1 and 4. We can see they hold constant. So anything that happens with my H plus will be shown in my rate. Okay, so we're going to take experimental 1 and 4. When we do that, we see that I doubled the concentration of H plus, and what happened to the rate? It did not change. It had no effect on the rate. We know that that is an indication of a zero order. So this implies zero order dependence with respect to H plus. Mathematically, put in my concentration on my rates, 1.15 times 10 to the minus 6 molarities per second for both of them. 0.1 molarities for my H2O2s, 0.010 molarity for my I minuses, and my 0.001 molarity for my experiment 4 to my 0.0005 molarity for my experiment 1. We see that my K's cancel, my units cancel, my hydrogen peroxides cancel, my I minus cancels, leaving me 1 is equal to 2 to the Z. Okay, well the only way that that can be true is that it has to be 0, but we can do it by logs. Log of 1 equal to Z log of 2, which gets me Z is equal to 0. Now at any one point in time I didn't have to get the other value reactants to cancel out. Once I knew the order, I didn't have to get them to cancel. However, it simplifies the math. It's a lot easier to go ahead and get those and cancel them out. That way it's less math as you work through your problem. Well, now I have the orders mathematically. I have to now figure out the K. Okay, how can I figure out the K? Well, I would take any one of these experiments and plug in the data. So, our rate law, we know final rate law is equal to K, concentration of my hydrogen peroxide to the first order, time the concentration of I minus to the first order. We also have H plus to the 0 order, but n to the 0 is 1, therefore we don't have that as part of the rate law. So I'll take this rate law right here, and I'll take some data. I'll probably take experiment 1 data, plug it in, and solve for K. We can now calculate the rate constant by substituting our values in. So using experimental 1 data, I'll plug in my rate, which is plug in this data right here. So I'll plug in my 1.15 times 10 to the minus 6 molarities per second, equal to K, time my concentration of H2O2 to the first power, time my concentration of I minus to the first power, and I'm leaving off the H plus because it's to the 0 power. I will now take these values and divide through to the other side, which gets me 1.15 times 10 to the minus 6 molarities per second over 0.01 molarity times 0.01 molarity. Okay, now my units, this molarity will cancel, which leaves me a molarity in the denominator and the seconds in the denominator. Do my math, it gives me 1.2 times 10 to the minus second molarity minus 1, seconds minus 1. That's my K. I can plug that into the whole rate equation now. I know that rate is equal to 1.2 times 10 to the minus second, molarity to minus 1, seconds minus 1, time the concentration of hydrogen peroxide to the first power, time I minus to the first power. So this right here, this equation, if I know the concentration of hydrogen peroxide in my iodide ion, I can plug those in and I can determine the rate anytime in the experiment. Homework 7 gives you data where you have to compare your rates to determine the order in respect of your reactants and the K of the reaction as well.